Cool. Hi, everybody. So this team is a collaboration between Make, Architects, and Arup. So Arup don't normally need an introduction, but we'll do a little one anyway. So we have Georgina joining us from Arup in London. So she brings some facade designing expertise to the team. And Make, we are a predominantly London-based architecture practice. There's about 150 of us internationally. We have studios in London, Sydney, Hong Kong, and Shanghai. The team here today have come across from London. And yeah, so we've had a lot of fun, and hopefully we're going to try and show you some of the fun we've had on this journey. So, okay. Which one? Sorry. Should we try again? Is that me? Yeah. I think it was me. Cool, that's fine. That's working. Great. So the kind of conversation with Boston Valley started a few years ago, where we actually worked with them on a project in London. So we've worked on a couple of projects with Boston Valley directly. So this is in central London. So it's part of a multi-use scheme, which is residential. It's called Rathbone Square. So they Boston Valley developed these amazing arches alongside our team in London. It's also part of the Facebook headquarters in London, so it's kind of this interesting mix of residential and office. And it's based on a courtyard design, and the two tunnels are these amazing public gateways into those spaces, and it's a super popular lunchtime spot now, and everybody stops and takes these Instagram photos. But on the other end of the spectrum, on the other side of the world, we've also worked with them on a heritage refurbishment, which is called Shell House. So this is in Sydney, so part of the wider Brookfield Place scheme, which is the tower as well, and it's a train station beneath. So highly complicated. So this was a facade retention scheme for the heritage asset, and the faience was what was Boston Valley's expertise was brought on board for that. So we kind of worked with them across the world, and it's kind of nice to come here and see their facilities, and that's been a great opportunity. So this is the crack team. So we have myself, Jack, we've got Nick and Andrew from Make, and then we've also got Georgina and Luca from Arup. So Georgina's here, but sadly Luca is not. So we had a lot of fun. So the project is kind of a continuation of a previous project we did as a research project we did together, which we called Hydroskin, and this was based off an internal Arup collaboration competition called Facades of the Future. So what we're looking at here, and this is where you realise it's another water-based project. So we were looking at on a large city macro scale how we could start using these vertical surfaces as a more productive way of gathering water, maybe using it for to start taking data points from it and recirculating it, so harvesting it, reusing it, and in different methods. Now, to be honest, we didn't really get much further than this level of detail at that point, so it's quite nice to dive into the detail of the actual facade panels. So, as you've heard this afternoon, vertical surfaces make up the vast majority of our surface area in our cities, and this is central London now. And what if we could do something with those vertical glass and brick and all types of facades, and whether we could use that productively. So on top of just gathering water, could those be elements that enhance growth? In the UK, we're having a lot of conversations about urban greening at the moment, and it's being encouraged, and it's a planning policy where we have to hit a certain amount of greenery on the facades now, essentially. So it's like, can we cross those two together, looking at water retention, which encourages growth? This is just your normal Tuesday afternoon in central London at the moment. So it's nice to be here. So it's basically, can we mitigate stormwater runoff to stop having our Tuesday afternoons like this? So the project brief we sent over to Boston Valley was basically what can we develop that looks at harvesting the rainwater, maximizing the inherent properties of terracotta, whether that's using glazes or not using glazes, to kind of create a new facade topology that can start to mitigate against some of these effects and passively encourage, greening potentially. So that looks at the porosity and the glazing as kind of a binary system, which you'll see develop. So these are some of our it's quite nice to see these snaps. So this is the aerial view you get of Boston Valley, looking down on these two. And then this is the workshop that Lex was discussing earlier. So we have a very messy workshop in the studio, but it was great to have that stuff shipped over from Andy. And Luca loves pointing at things, so he's over there. So you can see a little bit of the story of how that developed.
Delving into the research now. So, while working on the hydroskin concept that we started working with Make, we started delving into the bioreceptive materials. And for those who have never heard of the term, I will briefly say that it's the ability of materials to be colonized by microorganisms. And how do we do that? How do we, as designers, architects, steer this biogrowth and actually control it? So by engineering this set of material properties, that we first of all need capillary porosity for the water to be able to be absorbed and retained. And we also need a neutral pH that, since terracotta is a natural material, we are good to go with that. Our team focused also on the treatment of the texture and the surface roughness. And how did I manage to work and inspire Make was my personal research thesis that I did back in the TU Delft not so long time ago, that I had this crazy idea of creating porous glass through the process of foaming in order for mosses and microorganisms to colonize. And actually, the driving reason behind this was to incorporate as much as glass waste streams that are currently being landfilled now. So I created these samples, I soaked them into water, I dried them, I checked the permeability of them, I crushed them, and finally, the most exciting part of it is that after even 6 weeks of leaving them at the Botanical Garden of the TU Delft, I actually spotted life on them. So it was one of the most exciting parts. And that's how all this knowledge helped me when we sat down on the table with Make and we started asking ourselves, how much water can our facades capture? How can we answer that? We set out a strategy of really specific steps, gathering weather data that we first of all need the precipitation levels of each area to know how much water falls on any location that our building is. Then we need the orientation of the surface of interest that goes hand in hand with the wind and radiation levels, because actually the prevalent wind that falls onto the surface area onto our building is actually what has the force to change the rain trajectory and actually enable water to fall on our buildings. Because maybe, contrary to some people's belief, on vertical facades, water doesn't fall from rain that much, in contrast to when you are on the streets. And also, we need the radiation levels because we need to answer, so how much solar exposure we get and what kind of microorganisms will eventually grow. And this is when you mix all of these magic ingredients together, you can get such kind of a diagram that it's an expanded elevation of the building envelope. And the information that we get here, because I have included just a generic case of when the wind falls onto the corner, and you can actually see that the water zones and how much water we get onto the facades is really different. So this kind of input and this kind of information can really determine where we want to direct the water and how can we actually take advantage of this phenomenon. And this is another case that we have a more homogeneous pattern because the wind falls on the main facade. And then combining all this to some previous research that has already been done in the UDelft by Cassie, she explored with experiments bioreceptive concrete and actually did some CFT analysis on these horizontal microgroups that could actually tell which was the optimum design and which was the optimum ratio of the depth and the height in order to get as much water absorbed and delay the water flow. So after all this, we have come and with certainty to combine this set of new design principles for bioreceptive materials, that what we want primarily is the surface to be sculpted in such a way that we have a continuous water flow. Then we have these horizontal microgroups that actually are super important for the microorganisms to anchor themselves and attach on the surface. Okay, this microphone doesn't want to stay there. And finally, to remove the fire skin of the terracotta to actually enable the inherent porosity of this material to absorb water. And finally, I hand him to Andrew.
Thank you.
Maybe stay away.
I'm not going to. Hi, everyone. So we took all of that amazing research and started to look at how that could be translated into terracotta. Even from the earliest studies that we did, we always wanted to look at something that was relevant to both new build and also retrofit applications. So you're probably not going to hear too much from us about the substrate. That's intentional. At the heart of the form is obviously this idea about controlling water, but we want to do that in a really beautiful way. And I don't just mean that aesthetically. We also want to make a positive contribution to the natural environment and also deliver something that's topologically optimized, so it's as low embodied carbon as possible. We're also really interested in scalability, so trying to kind of minimize variation, but look at single elements that perhaps just by way of how they've been oriented can provide different functions, so inherent flexibility in that. I think these were some of the earliest sketches that we shared with Boston Valley. So you can see here we were initially exploring these kind of hourglass forms, looking at, one side might be glazed, the other side might be quite rough. Maybe it's got these kind of open ends that can kind of collect water. A glazed surface that can track the water, and then this rough surface that encourages the biocolonisation that Georgina mentioned. But that scalability point, actually, these are really just the same element that can be layered on top of each other and rotated. That then evolved into, this is a different model? Maybe it's in I think that's never mind. One of the issues with that concept, though, was that we didn't feel like we were actually addressing our own brief about directing water. So the next iterations really looked at more channel-like forms, so these kind of U-shaped baguettes that could literally direct the flow of water across a facade. There it is. There we go. That one should have come with the last one. It was really similar, but here we were looking at kind of spherical insertions in the ceramic, which could be oriented one way to kind of reject water, oriented another way to accommodate water, but also like the last question, actually, this is a great opportunity for accommodating plants or wildlife habitats as well. Boston Valley really do not like when you try and support ceramic off other ceramic. That was the other killer for these ones. So back to the point about trying to direct the water. We sort of evolved to something more like this, where again you can still see we're holding on to that concept of alternating the glazed and unglazed. In this case, a slightly more conventional convex concave form. But even in this really early graphic, you can see that we're being quite rigid with the horizontal. So actually being able to deliver something that's highly responsive to quite specific climatic conditions, this is not really doing that. So we started to try and introduce a little bit more variation in this. Again, Boston Valley were amazing in sort of making some suggestions to kind of set us off in different directions. So in this case, we were looking at only using extrusions, and all the variation comes through cutting them at different angles. That started to raise questions about material waste and things like that. But even within that, we started to get a little bit more expressive, and that really did lead us to the final concept that I'll talk through now, if it's going to work. Slightly nervous now. I do have faith, Georgina. There we go. So it starts with the water flow, all about these kind of ridge lines, these highly glazed elements that direct the water. That water then seeps into these island panels in between. So these are the really rough, unglazed panels. They have the grooves in them so that when it rains, that's where we really get our biocolonisation to take hold. It is a really expressive pattern, we think, but it's still highly modular and highly repeatable. Actually, this expanded vocabulary is 10 parts, 5 for growing, 5 for water direction. Boston Valley were kind enough to produce 4 different types for us for the mock-up, which gets us to that panel that you see today. Over to me.
So now that we have designs back in the a strong concept and we have a shape that could work on it, we need to try and build it. And the first step is to model it, but always trying to understand or take into account how the material actually behaves. How is it meant to be built? So I took notes all day and I almost lost them. There you go. Sorry. So one thing that we always need to consider is that this is a visual mock-up. So if we try to describe these pieces, they would be different of a full production model. The pieces that we see here today and in the screen are on a scale of 1 to 3. However, the pattern that we optimize using all your research is actually 1 to 1. In a full-scale production model, we're thinking we can make these pieces out of extrusions, the growth pieces, and the triangular shape. I don't know how to point.
Yeah.
This one, which is actually an intersection of the other two, would be a pressed piece. So as you saw in the main pattern, we are achieving what we think is a high degree of variation just by configuring a very limited number of pieces, which is always a nice thing to tell to your client, I guess. Yeah. This is our initial setup where we were thinking how to hold the piece in place. And if we see this is part of our study. This is the assembly that we settled on. But we studied multiple ones to check which one was more representative of our concept and which one used or tried to optimize the number of pieces that we used. We 3D paint a lot of them and had a lot of fun painting them, but that brings me to well, this little video just showing how the model is actually taking into account some tolerances, how far they need to be apart, how they can be assembled, where is the pattern, how if we're going to remove the fire skin of this piece, that piece actually needs to be modeled with a little bit of an extra layer. So the final piece is actually what we want to achieve. So a complex system doesn't have to be complicated. It's relatively a very simple model, but it has a lot of small thought into how it's modeled so it can be produced. After we have this, we start receiving all of this like box of candies from Boston Valley. I'm sure we all experience the same sensation with a bunch of very, very interesting glaze options. We settled on a very sleek glaze for the top with this speckled effect that kind of runs over the surface. Talking yesterday with Andy, he told us that effect was very desirable, not usually achieved by the use of lithium in the mix, but that is these days very hard to procure. So our system doesn't use it but achieves the same effect. I don't know exactly what's going on there, but I know a guy that does and must be here in the room. And for the other piece, it's actually just fire, and we remove the first layer of the fire layer as you described. So we kind of like that hard contrast between the two pieces, and we think it enhances the pattern. And if we imagine this aging and going slightly green, and with things growing on it, I think it would be a very nice contrast between a highly sophisticated finished surface and this growth in these other pieces, taking hold of the rest of the wall. Sorry, something that I need to say in this one. A full production model of this system, the way we see it, is a precast system. It's not a rain screen. We're trying to design in such a way that we minimize the use of aluminium. The pieces would need reworking, and they would be slightly different to work with a precast system. But that's why we have simulated this grouting. Whole concept actually depends on it, because we don't want the water to go into the screen. We need to seal it. And precast is well the support system that would enable that. Something that we also want to explore, or we think is important when designing with terracotta, is try to match the life or expected life of the terracotta material with the expected life of the support system. Because as we saw in one of the presentations yesterday, is the weakest link where you need to design for. I think I talked already too much, right?
No.
Yeah.
Yeah. Thanks so much. So you can tell that we've had so much fun as a team. It's been amazing to be here. Clearly, there's still lots more work to come. I mean, this was a very tangible output from that initial Hydroskins project that Jim talked about, and we kind of want to carry on that journey. We've kind of taken a very big leap from a theoretical position to a kind of tangible output. So now we really want to go back and analyze what we've actually done. We're going to try and persuade Boston Valley to let us leave this mock-up outside for a little while so that we can come back and see it in a year's time and actually then compare that with the data. If nothing else, we need to also simulate rain that's a bit smaller, I think. It kind of looks like we're throwing snowballs at it. So we're going to work on that too. That is definitely a next step. But yeah, like all the teams, I think we're really excited about actual real world project applications for this. You know, I talked earlier about this expanded vocabulary of parts. So how do we deal with openings? How do we deal with buildings generally meet the ground in a straight line? How do we kind of deal with that? So lots more development to come, but we're just so excited to carry on that journey, I think. So I think that leaves me to just say thank you so much to Boston Valley and the whole team there. Of course, to University of Buffalo, definitely to Wade. Wade has so many more skills than just driving forklift trucks, but he did us so proud to not break this on the way. Thank you also to our students, Sophia and Laura as well, who were amazing. Obviously to Andy as well on all the glazes, and Mick as well. What an inspiration you've been for us as well. And that's it from us. I really hope we'll see you in London soon.
Okay, questions?
Can I just leave this up? Is that great?
Thank you. That was a wonderful presentation, and I enjoyed watching this project come together. I love the kind of giant drawing template that you guys had. It's great. I had a question about the bioreceptivity, maybe for Georgina. And you know, this is something I've been working a lot with students and research on substrates and bioreceptivity, and especially in New Orleans, hot, humid climate. And one of the biggest kind of paradigm shifts that we try to talk about and advocate for is kind of like what one person's what might be a pest or a annoyance or gross for a human might be a dream for our more than human friends, right? And I'm wondering just if you've thought about that and like kind of more of a kind of conceptual question, I guess, about how we can try to kind of push back a little bit against the regime of like sanitization and everything that we've been taught, and kind of unlearning our what we've been taught about what can live on in and on buildings.
Thank you very much for this question. It's actually, a constant fight that I have with some people that are really reluctant when they hear moss. Oh, it's mold, we don't want it. But I've always said, and that's how I started in the TU Delft in researching on that. It's something that it's already there. It's going to be there. And instead of thinking how you are going to clean it, just engineer the way out of it, right? And so I was really lucky, I would say, that it happened to have in my hand some research that was already done, and this was what inspired me, that by engineering the porosity of the materials, you could actually control where it will grow and how you can steer it, and then the one microorganism will bring the other one, and the whole ecosystem will eventually take place. And what I actually was emphasizing when we were working and in all of our discussion is that this might be it's not here anymore. Here, this might be a pattern on a facade that it will have a seasonal growth. So let's think about that, because we cannot control, don't have enough data yet, things are under research. So mosses that will grow in our humid environments will also dry during summer. And how will this panel look like? And this all became part of the design process. Yeah.
To kind of a little bit further to what Mick was talking about the acceptability of imperfection potentially, and this kind of builds upon that. So it's a conversation we're starting to have with clients where, what it is okay to let stuff grow on the ledges, and the imperfection of the glaze is also part of its beauty. And that binary reading is a great demonstration of that, which we'd love to show everybody. And also, please come and touch it and stroke it, because the texture is brilliant. Yeah.
I actually did get an opportunity to touch it, and the texture is pretty cool. But anyway, so my question is also regarding the bioreceptivity of the structure. Specifically, we live in a world where we clean our buildings with detergents and chemicals that contain a lot of salts. There's acid rain and other kind of pollutants that come from our cars, from our factories, so on and so forth, that gets into the rain. How does the porosity of the terracotta interact with these environmental factors, and does the directionalized geometry and the controlling and pushing of the flow of water over the porous structures help to self-clean and regulate the kind of cultured ecosystem in the structure?
Okay, so quickly, I will answer to this, that the key is it lies on the moss growth and on the microorganisms. That's the answer, I think, to this question, because we didn't expand on that because we saw that many previous participation in last years actually analyzed it very thoroughly, like what are the benefits of moss, the air purification, the stormwater management, lower surface temperature. So once things grow, we are aiming, and that was one of the driving reasons why we did this concept, is that in order to mitigate to all these phenomena, and I think that and the contrast between this slick and glassy surface that requires very low to zero maintenance, I would say.
I guess you're the second. Oh gosh, this column is bad. I'm going to need to do this and look like the picture. I guess it's probably more a question for Boston Valley in terms of, what does acid rain do to the kind of structure or performance of terracotta? But obviously Buffalo is so blessed with so many terracotta buildings, but also this is a big manufacturing area too. So, obviously over time things do get replaced. Guarantee building is probably the prime example of that. But it is a highly durable material, clearly, that it thrives here. But also I would probably add that could potentially be part of our testing process as well, and that actually we just need to get it outside, let it get dirty, not be too precious about it, and see what it does. Yeah. And the moss apparently is the filter. It's all about moss. It's a great question though.
You have already asked this question of Boston Valley, but are there other patterns to test at the same time?
Well, I think we'd definitely love to. Yeah. 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 I think part of it, like I said, we have come definitely from a theoretical position. So clearly the pattern could be optimized further to actually understand. We'd love to have a universal kit of parts that you could deploy anywhere in the world, but it's the configuration of them is what's actually responding to the climate of that location. We just need to do more research.
Orientation of that same building.
Yeah. Actually, there's so many super hyper local variables as well within that. Lots more research to do, I think.
And one last question. Super interesting project. Having been part of last year's Henning Larsen's team, trying to grow moss on this terracotta screen, I had one specific question in terms of the moss growth on a textured surface. What do you think is the most successful trigger that could actually accelerate or actually promote the growth there? Do you have to sort of pre-apply some sort of mold cocktail onto the surface, or do you I don't know, especially your research based on the porous glass? I think that was fascinating as well. You were it's not supposed to grow there, but it grew, so it's amazing.
Happy to have a chat about the glass afterwards. I have brought some little things that I did from my research because it's quite a lot of information to actually be put in 15 minutes. So if we would do an accelerated biogrowth test, then we would indeed apply moss. We would leave it at a very humid spot. We would control the environment and the moisture of it. But actually, I think the smartness of this design is that we could leave it outside, and I'm really sure that because of the roughness of it and these microgroves that I call them, in an environment with lots of water content, things will inevitably grow, and that's the whole design and philosophy of it.
Yeah, I think that's hypothetically great. As a person who'd been manufacturing Core-10 facades for architects, both interior and exterior, they want to take a photo on day one. They don't want to tell them, in 6 months to 2 years, this is beautiful. They don't want to hear that. So actually, when we're producing pre-rusted Core-10 facades, we're actually in our factory blowing up like a big balloon and running like farm equipment over it and pre-rusting these panels. Now, nobody told us how to do this. We just had to figure it out. So I can actually imagine the exact same setup, identical setup, but with these panels. And instead of like a kind of vinegar solution like we had used, you sort of plant your moss bacteria or whatever it is. It maybe takes longer, but it's effectively the exact same process. Then you take these pre-mossed panels, you stick them on, you say, have a nice day.
Yeah, that's true. I think, no, I mean that this is what we like very much in this design and of the glazes that Boston Valley Terracotta produce, is that even if it stands like this, we like it personally.
Sorry, I know that happens and it happens with wing walls and things, but trying to understand or making that shift that things are seasonal they change with time. They age differently depending on each material. Is something that we learn to accept with time. I understand that pressure, but what we're trying to do with the pattern, let's say, and the design of the pieces is that the piece on day one also looks, in our opinion, beautiful. So if it is appealing from the beginning, I think it's easier to accept that variability over time. Yeah.
I think also these diagrams, I don't know if I will go there easily, that show the water zones of the building envelope. They could immediately tell where the growth will start first. And then by the time, and yeah, actually it will take more than 6 months. Yeah, this kind of diagrams. But since I managed to get moss on glass, on foam glass, we can certainly have in terracotta.
Okay, thank you very much. Yes.